In example 1, we're asked to graph and analyze g of x is equal to 2 log base 3 of x. There's a few different ways to do this problem. One thing that you should do, though, is before you even graph this thing, is think to yourself, what do you think it's going to look like? So what I'll do here on the right-hand side is I'll just make a little coordinate plane. And we know that the graph of, let's say, log base 2 of x, without this 2 in front, and if that was a 2, would look something like this. We're expecting this graph to look something like that. If we take a look at the equation, we have a 2 hanging out in the front, so that's going to narrow or widen or shrink or stretch the graph. And then the 3 is going to do something similar. It's not a 2, so it's going to change a couple values. But in general, the shape of this graph is going to look just like this one in red. So let's try to figure out exactly what this graph will look like. And we're going to plot some representative points to make that happen. One thing I like to do is I like to solve for x in this case. So what we will do here is we will try to isolate the logarithm first. We need to divide by 2. So we've got log base 3 of x is equal to y over 2. And then we're going to change this into exponent notation once you've isolated the log. So the base is 3, the exponent is y over 2, and that's going to be equal to x. When we write our table then for this, remember that g of x here is just our y values. What we can do is we can look at this exponent up here and pick good values that'll help us to graph this logarithmic equation. You can go straight from the log equation if you like. I just think that it's a little bit easier if you can solve for x and then change everything, when you do that into an exponent notation. So we can see here that y divided by 2, if we want that to be negative 2, then y would have to be negative 4. So just choose nice values that allow you to work with this. So 3 to the negative 4 divided by 2 power, which is 3 to the negative 2, that would be 1/9. If we pick another nice value to use, negative 2, and really anything will work here for this exponent, but it's just nice to pick values that work out well for us where we can do this by hand and we don't need a calculator to evaluate this. So for negative 2, we'd have negative 2 divided by 2, which is negative 1, and 3 to the negative 1 power is 1/3. 0 is also another nice one to pick for y. Again, we're starting with the y values and then seeing what the corresponding values of x are. And so 3 to the 0 power, 0 divided by 2 is 0, would be 1. If we continue on, we can do a little bit more here. We could do 2 maybe, and then 4. So 3 to the 2 over 2, which is 1, so 3 to the first, that would be 3. And if you take a look at the pattern, you can kind of start to see what you think might happen here. We've got 1/9, 1/3, 1, 3, and then 9 is probably the next one, and you'd be right. 3 to the 4 divided by 2, or 3 to the second power, is definitely 9. To graph this then, what we can do is just use these as our x and our y. So we've got 1/9, right 1/9, and down 4. So that's going to be super, super close to the y-axis. 1/3 and down 2, so it's going to be right about there. 1/0 would be right here. 3/2 would be right 3 up 2. And then 9/4. So we could go right 9 and then up 4. So the 3 part of the log equation, the base, is causing our x values here, if we pick nice values to work with for y, to be some power of 3. The 2 is spacing things out a little bit. So instead of going right 3 up 1, we went right 3 up 2. And instead of going right 9 up 2, 3 squared would be 9. We're actually going to go right 9 up 4. So it's just doubling all the values of y if you want to think about it like that. Or in this case too here, we would normally go right by 1/3 and down 1 if there wasn't this 2 out here. And so we're going to go right by 1/3 in this case and down 2. So all of the y values are just doubled. If we connect these all together, we can go ahead and get a shape of the graph. Remember that this graph won't cross over here. won't cross the y-axis. And that is because there is no shift here. If there is a shift left and right, if there is some number right next to the x in that argument position that's part of the logarithm, that shift will cause the vertical asymptote, in this case, to shift left and right. Remember that there is no horizontal asymptote, there's just one vertical asymptote, and it's right here at x is equal to 0. So if we do a little analysis, we could write our asymptote for this as x is equal to 0. That's a vertical line straight through 0. And the domain, those are all the possible values of x, and you can see that the graph will never hit this value of x here, which is 0, and it doesn't exist for any negative values. So the domain is going to be 0 to infinity only. The range then is going to be all the possible values of y, and you can see that this graph will definitely exist for all values of y. And it looks like it would kind of level out here, but it really doesn't. And you can see that because as we pick larger values of y, this part here just becomes bigger, which is x. So if we just pick really big values, we're going to get correspondingly larger values of x. So the range is negative infinity to infinity. Also, relate this back to the inverse of a logarithm, which is an exponent. And your exponentials, your asymptote will be y is equal to some number. If there's no shift in that case, in the up or down direction, then it will be y is equal to 0. So for a logarithmic graph, it's x is equal to some number. And if there's no shift in the x direction, left or right, then it's x is equal to 0. The domain is just like the range for an exponential, and the range is just like the domain. So you can think about it as just the x's and y's are being switched.